Good afternoon, everyone. Thank you for coming to the class. This is ME 585, System Identification and Adaptive Control. With that, I would like to just give you guys some motivation, perhaps, to take the class. And the motivation, these examples will be drawing from something that you observe every day, as well as some projects that I have done. So, one thing that amazes me always is how humans learn and adapt. Oops.
Have you ever wondered how your child learns language? They start by copying their parents. Imitation occurs in early development and is a crucial building block to language development. In fact, infants are able to imitate early facial expressions within the first few days of life.
You see, copy.
Vocal interactions by 4 to 5 months. They coo, they cry, and rattle. By 8 months, babies
Copy.
will copy familiar gestures such as clapping and waving. By 18 months, children begin to imitate simple actions such as banging with a toy hammer.
Right? And there are many videos that look like this. Not just humans, but animals. They also learn and adapt, right? It is amazing. This seems to be a natural ability or capability for humans to do. And then how we can do this for machines, right? That gives us some motivation to learn about adaptive control. Adaptation is the key word here. It's the ability for a system, whether mechanical or human, but some kind of system to be able to adapt to uncertainties or changing environments. And that power, I think, is pretty strong, right? And I took some of the projects that I have done in mechanical system domain. Some of these projects are very, very high precision, below nanometer scale precision. Some of these machines are very, very large, hundreds of meters in scale. But the common thing is we want these machines to have certain kind of intelligence. And here are some examples about this kind of intelligence and how adaptive control and system identification is useful. The example here is a few years ago, your computer would still have the hard disk drives. Now they go to the enterprise storage, the cloud. But they all have this common scenario. This is a nanometer scale precision system, sub-10 nanometer scale, position error tolerance. And these disks, they spin so fast that the airflow inside this mechanical enclosure is very sensitive. And if you tap your hard disk drive quickly, you may fail at this drive. There are incidences where the bank, all the hard disk drives somehow they all died because there's a construction next to the bank, and the vibration from the ground just makes this mechanical system fail. And it's a very complicated process. Amazingly, they still work. $70, right? They can do terabyte of storage. But the problem that they face is very, very challenging. Vibrations happen in different frequency regions. And these complex aerodynamics makes it very difficult to know exactly where these vibrations happen. And different products, they may change these vibration characteristics as well. And these are very general problems for precision manufacturing. So in data centers, they have this problem. They call this so-called audio or acoustic vibration. If you've ever been to a data center, you will know it's so loud, you cannot bear to go inside without wearing a headset. So the problem is actually more involved than you would think. As engineers, we solve a problem by looking into the details. So the problem is actually, it's not really the voice or audio that impacts these mechanicals, creates the vibration directly, is because if you have a very loud noise, it's going to shake the mechanism, shake the mechanical mechanism. And that shaking mechanism can create, for example, resonances, resonant behaviors. And that will break the mechanical system. All right? And this is even more challenging if it's acoustic or audio related. Acoustic is something interesting in the sense that they are very broader band. You can see here hundreds of hertz in the width. And then there are different bands. Human voices, if you take a recording, you will see it's actually spreading in a broad range of frequencies. There are multiple resonances and wide spectral peaks, and they depend on environment as well. So these wide band frequency vibrations is actually a very big headache for any precision mechanical systems. Another system that is relevant is you will see, you can imagine these in real life scenarios. You have suspension system in the cars. Without suspension, if you have driven an older generation of cars, you will see it's very bumpy. So active suspension is very important. It's very important to be able to isolate vibrations from precision machines. These vibrations can be from the road or can be from other factors from the environment. All right. So the basic mechanism about this active suspension is I think it's like boxing. It's like you predict the person who you fight, maybe the road. You're trying to fight against the road. If there is if someone is trying to punch you, you may take a few punches at the beginning, but you may be able to dodge it as you learn from the pattern of these vibrations. So once you can do that, there are something that you can do. So you can, adaptive control can enable you to accommodate these vibrations. This is without active adaptive control. This is with active adaptive control. This is the baseline noise, and this is the performance that we can gain from adaptive control. You can see basically we have removed entirely the vibrations. You can see this from the time domain. You can see this also from the frequency domain, where these black dotted lines have been completely removed. Black dotted for the bottom two figures, red solid lines in the top right figure. So the way that we do is essentially using techniques in this class. Vibrations are frequency dependent, so adaptive control enables you to be able to predict the vibration frequencies. It actually enables you to be able to follow even if the frequency will change for these vibrations. This is for the case if there's a single frequency component. This is also the case if there are multiple frequency components. And it is happening very fast as well. So you can see this is within seconds. Within probably milliseconds, we can do these adaptations very quickly. And this is the time domain performance. So that is for this active suspension system. This is also the case for the previous mentioned audio vibration rejection problem. At the beginning, we don't know anything we don't make assumptions about the vibration frequencies. We just learn. So the adaptation kicks in from here, and very quickly we're able to find there are 3 peaks in these vibrations, and then the frequency of these peaks are identified, and then after that you can apply controls targeted at these frequency components of the vibration. And then on the bottom, this is the results that you can achieve. Okay, so the beauty about adaptation is you can do this not just for a single case, but you can do this for different types of vibrations in practice. So you can see 4 different cases here, and then the results is pretty significant for the nanometer scale precision devices. If you compute the 3 sigma value, is actually 34%, which is very difficult to achieve with other techniques. If you do PID, impossible to be able to accommodate these kind of strong vibration components. Okay? So some detailed illustrations of how it works at different frequencies. And this is the time domain results. So each plot here, top is without adaptive control, bottom is with adaptive control.